The technical feasibility study phase of a microgrid development project is where the information collected during planning is significantly expanded and hardlined. Costs for this phase are significantly higher than for planning, even possibly requiring their own financing, and the expertise of professional engineering consultants will be required. The goal of the phase is to create a technically detailed, economically feasible community microgrid plan that can become the basis for soliciting financing. A technical feasibility study for a microgrid is often also referred to as an audit grade study. In essence, it broadens and deepens the microgrid development plan that was created at the end of planning. This early stage plan would include a preliminary list of potential sites for the microgrid, a preliminary list of potential technologies that can be used in the microgrid, a very preliminary cost estimate including the cost of installation and operation of the microgrid, and a very preliminary version of potential business models for ownership and management of the microgrid. As noted earlier, a technical feasibility study will take this base information and significantly deepen and expand it over the course of the feasibility study. Key outcomes of the feasibility study phase, or the audit grade study, are a detailed design of the microgrid from a technical and economic perspective, a cost-benefit analysis of the proposed microgrid, a proposed ownership structure for the microgrid, and a financial plan. Let's unpack each one of these in a little bit more detail. The detailed design that will be delivered at the end of the feasibility study phase will include a final list of sites, those facilities that will be connected to and will use power from the microgrid. A final list of the generation technologies, from combined heat and power to solar to wind to storage, that will be used to generate power for the microgrid. A set of detailed design and engineering documents that will describe precisely how the microgrid will work, how the technologies will run, how they will connect to the microgrid, and then how the microgrid itself will interconnect to the overall electrical grid. And then finally, a detailed cost estimate of the cost to procure and install the equipment, the cost to develop and construct the distribution infrastructure for the microgrid, and ultimately an estimate of the cost to own and operate the microgrid. The detailed design data created in the first phase of the feasibility study will then be bench tested by conducting a cost-benefit analysis based on the information collected. The cost to be analyzed will include the administrative cost to run the microgrid, the capital investment necessary to procure the technologies, both generation assets and controls, storage systems, and the distribution and interconnection infrastructure necessary to make the microgrid work, annual operations and maintenance costs, and any environmental costs, assuming that environmental benefits are included in the cost-benefit analysis. On the other side of the analysis, there are two basic types of benefits that can be analyzed. Direct benefits, like energy cost savings, are relatively easy to monetize and fold into the calculations. Indirect benefits, like power quality improvements, environmental benefits such as reduced emissions, and increased power reliability, such as avoided losses during power outages, are real benefits but are a bit harder to quantify and include in the calculations. Nonetheless, both need to be included to measure the true benefits of a microgrid to a community and to a region. As noted on the previous slide, cost-benefit analyses can be complicated and require a lot of judgment as well as a lot of input. Luckily, there are modeling tools that have been developed specifically for microgrids that can help with this process. The Distributed Energy Resources Customer Adoption Model, or DERCAM, from the Lawrence Berkeley National Lab is one. The Microgrid Design Toolkit from Sandia National Labs is another. Homer Pro from Homer Energy, LLC, is a third. And there are multiple other proprietary and/or custom modeling tools that can be used in the creation of a microgrid. Clearly, during the technical feasibility studies, such modeling will need to be utilized in order to generate cost-benefit outcomes that are transparent and defensible. The next topic to be addressed in the technical feasibility study is the ownership structure for the proposed microgrid. This is a critical but often very complex issue, especially for a community microgrid which serves multiple different entities across multiple jurisdictional boundaries. 4 common ownership categories are: local utilities can own microgrids and provide services very similar to the ones they do now, but likely with a different cost and ownership structure. Local communities can own microgrids funded by bonds or other sources, assuming they are legally permitted to do so. Third-party service providers can own and operate microgrids on behalf of communities, and communities and third-party service providers, including utilities, can jointly own and manage community microgrids through public-private partnerships. All 4 ownership models have a range of variations and all are relatively complex, and new models are evolving in real time as the development and deployment of microgrids gains momentum. A key objective of the feasibility study is to identify the specific ownership model that works best for the circumstances in a given community and incorporate this model into the final microgrid development plan for the project. The last component of the technical feasibility study is the financial plan for the microgrid development project. The plan should, at a minimum, provide detailed estimates of both costs and revenues. On the cost side, the annual cost to operate, maintain, and own the microgrid over the service life of the equipment. On the revenue side, any customer charges that can be obtained, including anticipated rates, demand charges, etc., and any external revenue streams such as tax incentives, grants, solar, renewable energy credits, etc. Once the detailed design information, the cost-benefit analysis, the ownership model, and the financial plan have been developed, they can be rolled into a final microgrid development plan suitable to serve as a basis for seeking financing and procurement, the next phase of the microgrid development process.